And practice final number 2, part 2. We're working problems 92 up to 109. So this is Dimensional Analysis Central. We might want to get a zoom in on this little map that we used to use a little bit. So the idea from this chapter or 2, moles was the central item. Everything worked through moles because we could take moles and turn it into mass. Mass, we'd be looking for grams. That was the periodic table usage. Mass can become moles, moles can become mass. It works either way, but moles is central. Moles can also be turned back and forth into volumes. Volumes, we prefer liters. The magic number that got us from moles to volumes or vice versa was 22.4. And then particles was our third choice. Particles we could get back and forth through moles using Avogadro's number, 6.02 times 10 to the 23rd, which I think we stored in our calculators. It's probably still there. Particles are things like atoms or ions or molecules or formula units or whatever. So this little map we sort of used to get from thing to thing. If we had to get from volume to grams, we'd work from volume to moles and then moles to grams. Or if we wanted to get from grams to atoms, we'd work from grams to moles and moles to atoms. Moles was the central figure everything flowed through. This is Dimensional Analysis Central, so I started a little bit of the dimensional analysis already. Dimensional analysis, as always, whatever number is in the story we write here. It's ideal to write a number, a unit, and if you have one, like a substance, a formula for what substance you have. For this first one, it's iron 3 chloride. Iron has a charge of 3, because that's why it has a Roman numeral 3. Chlorine has a charge of 1, because it's in column 7, and 7s want to get up to 8. That's a difference of 1. And when we have different charges, we do a little swap to make the subscripts. But FeCl3 is that formula. But all of these, I wrote everything in the problem in that first slot. And then we're always looking to get an initial cancel. Whatever words are here, we need to cancel them by putting them there. And just pay attention to what's asked for in the problem and where we are on our map. So for this, we're trying to get from moles of FeCl3 to moles of chlorine. And so the numbers for this are just given by the coefficients. In 1 mole of that big thing, there's 3 moles of chlorine because of the little 3. Just multiply those numbers and we're good. Wise chemistry people may not even need the dimensional analysis structure. If you had the right formula, you'd realize there's 3 chlorines in every one of these. Just multiply by 3 and you're good. Second one, we need a formula for sodium carbonate. So carbonate, we should have memorized, has a charge of 2. Sodium has a charge of 1 because it's in column 1, so that makes the subscripts flip-flop. That's why that's Na2. But grams need to go, and we're asked to get to moles, and that's good. The number for moles is always 1. The number for grams, for NaCO3, we're going to need to use our table. If we use our table, Na, look that up, C is 12, O is 16, 16 times 3, add that all together, we should turn out 106. We'd be done if we wanted moles of the Na2CO3, but we don't want moles of Na2CO3. We want moles just of Na. In 1 mole of that complicated formula, there's 2 moles of Na, because Na had a little 2. As always, multiply everything on top, divide by anything on the bottom. 94, I give you atoms of sodium, so we need to get rid of atoms to hopefully create moles. Everything runs through moles. The number for moles is usually 1. The number for atoms is Avogadro's number. In this one, we are seeking moles, so we're done. Just this divided by Avogadro's number. If you don't remember Avogadro's number, again, it was 6.02 times 10 to the 23rd. This one, we have moles of CO2, so we need to get rid of moles of CO2, and then we'll see what we're trying to make, because moles can be turned into anything. Here we're trying to get grams. to go from moles to grams, moles number is always 1. Grams number comes from the periodic table. C is 12, O is 16, but 16 times 2, because there's 2 oxygens, that would be a 44 total. 496, you're given atoms, so we want to eliminate atoms, and we can always get to moles. The number for moles is always 1. Number for atoms is always Avogadro's number. If we're looking to get to moles, we'd be done. But we're not looking to get to moles, we're looking to get to grams. So to get from moles to grams, I have to cancel moles to get to grams. Moles number continues to be a 1. Grams number comes from the periodic table. For potassium, 39.1. 97, I'm giving you moles, so we can get from moles to anything. In this case, we want to get to milligrams. Well, the closest we can get is the grams for now, and then cancel grams to get to milligrams. For the first move, 1 always for moles. Grams for potassium is 39.1, as it was in the previous question. And then 1,000 milligrams make a gram. 98, we're going to start with moles, so we cancel moles, and we can make anything. What we're after is atoms. 1 is the number for moles, Avogadro always for atoms. 99, we start with grams, so we eliminate grams with a quick cancel, and everything's going to go to moles. 1 is mole. Grams on CO2, we had that earlier, that was 44 a couple problems ago, it's still 44. If we wanted moles, we're done, but we're trying to get the number of molecules. So we're going to have to cancel moles to get to molecules. 1 is continually the number for moles. Avogadro's number for anything in the molecule, atom, formula, unit, ion categories. 100, we have liters, so we're looking to get rid of liters, most likely going to moles. Again, 1 for all these moles. 22.4 is the number that goes with liters. Just divide that, and that's a quickie. 101, we have milliliters. Milliliters can't go anywhere other than liters. So we need to do 1,000 milliliters to make a liter. Then liters can make our best friend, which is moles. 1 for mole, 22.4 always for liters. To the back, 102, we start with liters, can get us the moles, using a 1 mole and a 22.4 liters. And then we are trying to get to grams. So then we need to recancel the moles to get to grams. The 1 for moles. Grams comes from periodic table. 12 plus 16 is 28. For 103, we have grams. Grams get us the moles. 1 for moles. Grams comes from periodic table. 1 for hydrogen, 35-ish for chlorine. Added up, it's 36.5. But we don't want to stop with moles, we want to get to liters. So a recancel of moles to get to liters. 22.4 always with liters, 1 always with moles. 104, we have liters to get rid of and get to moles. 1 for moles, 22.4 for liters. Then recancel moles to get where we want to get, which is to particles. 1 for moles, Avogadro's number for particles. 105, we start with particles and we can get to moles. 1 with moles, Avogadro with particles. But we don't want that, we want to get to liters. So we'll cancel moles to get to liters, 22.4 versus 1. Skip 106 for a second while we're in the dimensional analysis groove. 107, we're still doing dimensional analysis. We have to write a formula for ourselves. So magnesium's in column 2, has a charge of 2. Nitrogen's in column 5, So it needs 3 electrons to get up to its 8. With 2 and 3, we do a reversal, 3s and 2s. So we start off with grams of Mg3N2, and we can get to moles. 1 is the number for moles. Gram number has to come from the periodic table. Take magnesium's number times 3, take nitrogen's number times 2, 14 times 2, add that up, and you would get 100.9. But we don't want moles of Mg3N2. We need to get from moles Mg3N2 to moles of just Mg. So we're going to use the subscripts when we go from moles to moles. 1 mole for the crazy thing, 3 moles for Mg, because Mg had the little 3 subscript. Then we want to get from those moles to grams just using Mg. 1 on the bottom, 24.3 on the top. Back to 106. 106 is just more basic math. Percent compositions, to do percentages, you always, almost always, start with fractions. The bottom of the fraction, you need a total mass. The top of the fraction, we need a mass just for the one thing. So carbon's thing, there's 4 of them times 12, because mass on the periodic table for carbon is 12. 4 times 12 is 48. That's the top of a fraction. Hydrogen's mass is 1 times 6 of them is a total of 6. So that's the top of a different fraction. Oxygen, there's 3 times 16 from periodic table says 16. We're getting 48 there. That's the top of a third fraction. To do the bottoms, we need to add these up to get a total. If we add up all of those to get a total, the totals are 102s. And then you grab your calculator and you punch them in, and to make percents, you'll have to move over 2. So this is going to show up like a 0.47 thing. If you move the decimal over, you'll get 47.1%. 6 dividing 102 is a 0.05 kind of thing. So we'll get 5.88%. This will be a matching 47.1%. Every answer, remember, we want 3 significant digits. 1, 2, 3, 1, 2, 3, 1, 2, 3, and some kind of a unit. Here it's just a percent sign. But on the previous question, 107, we want 56.6 to get our 3 digits, and say grams, and say Mg. Like we need a number, a unit, and then a substance if available. So make sure you don't forget to have your HCl's and CO's and things like that on there. 108 is another one with just more like basic normal sort of math, not so much a big dimensional analysis thing. For these formulas, we always divide the percentage number by what the periodic table tells us for mass. For tin, that's 118.7. If you do 19 divided by 118.7, that'll show you a 0.16-ish. Iodine, we would divide by 126.9, and that would show us a 0.64-ish. We do both of those divided by the lower number out of these two, which is 0.16. So 0.16 divides itself to be 1. This divides 0.16 to be 4. So that tells us that tin, there's 1, and iodine, there's 4, and that's called an empirical formula. 109, we start with that same basic process. We divide carbon by its mass on the periodic table, which is 12, and that shows 6.98. We divide hydrogen by its mass, which is 1, that shows you 16.3. We divide those both by the lower number, the 6.93, and that shows you a 1 and a 2.33. These have to be whole numbers. So if you get a 0.5 kind of thing, you multiply them both by 2. If you get a 0.33 or a 0.66, those are thirds, multiply them both by 3. So that's a 3 and a 7. So we're looking at C3H7. If this were an empirical formula question, we'd be done. But we have to check the masses. In the story, it tells us there's a mass we're shooting for of 86. 3 carbons, 3 times 12 is 36. 7 hydrogens, 7 ones is 7. 7 and 36 is 43. And our goal was 86. We're only halfway there. The real answer is 2 times as much, C6 and H14. That's it for today. Hope that's enough. If not, email me, we'll Zoom, we'll work it out.